For generations, whenever scientists wanted the clearest view of the cosmos, they turned to space observatories like Hubble, James Webb, and Chandra. Floating high above Earth's atmosphere, these telescopes revealed a universe our planet could never fully expose. But now something completely unexpected has changed that story. A telescope that never left the ground has captured images so enormous, so incredibly detailed, and so unbelievably deep that astronomers across the globe were left stunned. Because for the very first time, the Vera C Rubin Observatory has finally opened its eyes. Before we reveal what Rubin discovered, make sure to subscribe to the channel and turn on notifications. We bring you the latest breakthroughs in space, science, and the greatest mysteries of the universe, so you never miss an incredible discovery. And what it recorded on that first night wasn't simply breathtaking, it was deeply surprising. It offered a glimpse into a universe packed with far more activity than anyone imagined. The sky appeared crowded, constantly changing, and overflowing with hidden structures, forcing scientists to rethink the way they chart the cosmos. At the center of this achievement is a camera roughly the size of a compact car, capable of recording an astonishing 3.2 billion pixels in a single shot. Every image spans an area wide enough to fit around 40 full moons, while the mountain of data it will generate over the coming years is so enormous that researchers may spend decades trying to fully understand it. Yet even the very first observations were already filled with extraordinary discoveries. Colliding galaxies caught in the middle of merging, regions where brand new stars are being born. Tens of thousands of ancient star clusters scattered across space, and in only 10 hours of observing, Rubin identified more asteroids than astronomers typically discover over weeks of searching. This is the milestone scientists have anticipated for years, a telescope powerful enough to watch the universe evolve in real time, detect sudden cosmic explosions as they happen, and uncover enormous structures that had remained completely invisible until now. Today, we're exploring the remarkable first discoveries made by the Vera C Rubin Observatory and why these historic images have sent shockwaves throughout the astronomical community. Long before it captured a single photograph, the Rubin Observatory had already earned an almost legendary reputation. Built high on Cerro Pachon in Chile, one of the driest, darkest, and clearest observing sites anywhere on Earth, it wasn't designed to simply take beautiful pictures. Its true mission was far more ambitious, to repeatedly survey the entire southern sky in a way no telescope had ever attempted before. Powering the observatory is the Simoni Survey Telescope, an advanced three-mirror system that differs from the traditional two-mirror designs used by most observatories. This unique architecture delivers an extraordinary combination of razor-sharp detail and an exceptionally wide field of view. Its massive primary mirror stretches an impressive 8.4 meters across, but Rubin's greatest advantage comes from combining these revolutionary optics with the largest digital camera ever constructed for astronomy. The camera itself weighs nearly 3 tons, measures roughly 3 meters in length, and records ultraviolet, visible, and near-infrared light with extraordinary accuracy. What truly separates Rubin from every telescope before it, however, is its incredible scale. A single exposure captures nearly 10 square degrees of sky, an area roughly equal to 45 full moons placed side by side. With just one photograph, Rubin can observe a region that would require thousands of separate Hubble images to recreate. And because it revisits the entire visible sky approximately every 3 days, Rubin isn't creating a collection of still photographs. Instead, it's assembling an enormous time-lapse movie of the universe itself, revealing flashes, explosions, collisions, movements, and transformations as they unfold across space. This isn't a telescope built to focus on one distant target. It's a machine designed to watch almost everything, all at once. When the observatory released its first images in June 2025, astronomers expected something remarkable. What they received exceeded every expectation. Following just over 10 hours of initial observations, Rubin unveiled an enormous image that researchers quickly began calling the cosmic treasure chest. The breathtaking mosaic covers approximately 25 square degrees and centers on the southern portion of the Virgo cluster, the nearest massive galaxy cluster to our own Milky Way. Constructed from 1,185 individual exposures, the final image contains millions upon millions of stars and galaxies. Elegant spiral galaxies stretch gracefully through space. Giant galaxies caught in the process of merging appear twisted together like streams of cosmic smoke. Immense filaments weave between distant galaxy clusters, forming the enormous web-like framework of the universe. And hidden deep in the background, visible only after magnifying the image, lies an ocean of faint reddish galaxies, each one potentially containing billions of planets of its own. As astonishing as this first glimpse appears, it represents only around 0.05% of everything Rubin is expected to discover. Over the next decade, the observatory is projected to detect nearly 20 billion galaxies. That means this incredible first mosaic isn't the main event. It's only the opening preview, the first scene in a 10-year cosmic documentary that the universe is about to reveal through the eyes of the Vera C. Rubin Observatory. As researchers examined the enormous mosaic in greater detail, they realized it offered far more than a stunning view of the night sky. It revealed the universe in motion, galaxies growing, interacting, stretching apart, and slowly evolving across cosmic time. Every corner of the image contained evidence of an ever-changing universe, captured with a level of detail so extraordinary that it redefined what scientists believed a first light image could accomplish. If Rubin's first mosaic demonstrated its incredible capabilities, the observatory's next release proved something even more remarkable, that a telescope operating beneath Earth's atmosphere could compete with some of the greatest space observatories ever built. The next showcase was a breathtaking wide-field image of the Lagoon Nebula, an immense stellar nursery located roughly 5,200 light-years from Earth. Most people recognize the Lagoon Nebula from tightly focused images captured by observatories such as Hubble, where the glowing clouds fill nearly the entire frame. Rubin presented a completely different perspective. Instead of zooming in on the nebula alone, it revealed an enormous panoramic scene, where this vast cloud, despite stretching nearly 55 light-years across, occupied only a small portion of the overall image. Surrounding it was an incredible tapestry of celestial objects. Brilliant star fields filled the background alongside open star clusters such as Messier 21, the colorful Trifid Nebula, the stellar grouping Bochum 14, and the densely packed globular cluster NGC 6544. Within a single photograph, Rubin captured objects separated by enormous distances and vastly different stages of cosmic history. Young stars were forming inside the Lagoon Nebula, while ancient globular clusters, born billions of years earlier, shone from far beyond. This remarkable view is possible because of Rubin's extraordinary field of vision. For comparison, Hubble captures an area of sky roughly equal to about 1% of the full moon in a single exposure. Rubin can observe an area equivalent to approximately 40 full moons at once, and despite covering such an enormous region, its images remain exceptionally sharp, rich with fine detail, and layered with hidden discoveries. For the first time, astronomers can appreciate the Lagoon Nebula not as an isolated object floating in space, but as one part of a much larger cosmic environment, a neighborhood where stars are constantly being born, aging, dying, and reshaping the galaxy around them. But producing breathtaking images was never Rubin's primary mission. Its real purpose is to transform the way astronomy is done, and remarkably, even during its earliest test observations, it has already begun fulfilling that promise. In just 10 hours of observing, Rubin discovered 2,104 previously unknown asteroids, including 7 classified as near-Earth objects. To understand how significant that is, consider this. Observatories around the world collectively identify roughly 20,000 new asteroids over the course of an entire year. Rubin could discover millions within only its first few years of operation. That would make it one of humanity's most powerful systems for identifying and tracking potentially hazardous objects long before they pose any threat to Earth. Asteroid hunting, however, is only one piece of Rubin's ambitious scientific mission. The observatory will also investigate 2 of astronomy's greatest mysteries, dark matter and dark energy, by measuring how galaxies gather, move, and evolve across billions of light years. Its rapid survey cycle will allow it to detect short-lived cosmic events almost instantly, including exploding supernovae, gamma-ray bursts, stellar eruptions, and countless other transient phenomena that previous surveys often missed. Rubin will also search for ancient R-Lyrae variable stars, potentially identifying around 100,000 of them to construct the most detailed map ever created of the Milky Way's distant outer regions. Yet behind every one of these discoveries stands an even greater achievement: data. By the conclusion of its 10-year survey, Rubin is expected to collect nearly 500 petabytes of information, an archive containing billions of celestial objects and trillions of individual measurements. Together, these observations will form an unprecedented time-lapse record of the evolving universe, a scientific treasure that researchers may spend generations exploring. The Vera C. Rubin Observatory isn't simply another telescope. It is an astronomical powerhouse built to reshape how humanity studies the cosmos. To appreciate why Rubin's first images surprised scientists so profoundly, it's important to understand one of astronomy's oldest obstacles: Earth's atmosphere. Every ground-based telescope must observe the universe through constantly shifting layers of air. Turbulence, changing temperatures, humidity, airborne dust, and countless tiny distortions blur incoming starlight before it ever reaches the telescope's mirrors. This challenge is precisely why observatories like Hubble and the James Webb Space Telescope were launched into space to escape Earth's turbulent atmosphere entirely. And yet somehow, Rubin is challenging that long-standing limitation. High atop Cerro Pachon, in Chile's Atacama Desert, the observatory occupies one of the most exceptional observing locations anywhere on the planet. The region is famous for its incredibly dry climate, remarkably stable atmosphere, almost non-existent rainfall, exceptionally dark skies, and virtually no artificial light pollution. These rare conditions have already made the Atacama Desert home to many of the world's most advanced observatories. Rubin takes full advantage of this extraordinary environment, pushing the capabilities of ground-based astronomy further than almost anyone believed possible. Working together with its revolutionary 3-mirror optical design, its enormous digital camera, and an automated system that scans the sky every night, the Vera C. Rubin Observatory overcomes many of the atmospheric limitations that have challenged ground-based telescopes for decades. The result is something once thought nearly impossible: images that are not only exceptionally sharp, but also incredibly wide, matching and in some cases even exceeding the quality of observations made from space. For a telescope firmly planted on Earth's surface to accomplish this isn't simply impressive. It marks a turning point in modern astronomy. It signals the beginning of a future where ground observatories and space telescopes work together, complementing one another as they explore the deepest mysteries of the universe. But one of Rubin's greatest breakthroughs isn't visible through its mirrors. It's hidden inside the enormous digital network built to handle the overwhelming flood of information the telescope produces. Every night, the Vera C Rubin Observatory generates nearly 20 terabytes of data, far more than traditional observatories can easily process. To handle this enormous volume, a dedicated 100 gigabits per second fiber optic network transfers the data from Chile to processing centers in the United States, where advanced software instantly calibrates images, detects moving objects, identifies cosmic events, and updates a constantly growing map of the sky. Rather than creating a simple collection of images, Rubin builds a living digital model of the universe, refreshing it every 3 days. It can detect exploding supernova, gamma-ray bursts, interstellar objects, and other unexpected events almost as they happen. This transforms astronomy from taking occasional snapshots into continuously monitoring the universe in real time. Like a city-wide security camera system watching every street, Rubin constantly scans the sky, ensuring that even the briefest cosmic events are no longer missed. Instead of focusing on a single street, every camera watches continuously, waiting for the unexpected. Rubin applies that same idea to the night sky. The scientific importance of this capability is difficult to overstate. Transient events reveal some of the universe's most violent and mysterious processes: stellar explosions, powerful collisions, the birth of new stars, and the forces that shape entire galaxies. Rubin is expected to detect thousands of these events, including many that have never been observed before. Each one could unlock new discoveries and reshape our understanding of astrophysics. Beyond its discoveries of galaxies and short-lived cosmic events, Rubin's early observations of RR Lyrae stars have already hinted at another major scientific breakthrough: the ability to map the Milky Way with unprecedented precision. RR Lyrae stars are extremely old, pulsating stars that serve as reliable standard candles. Because their brightness changes in highly predictable cycles, astronomers can calculate their distances with remarkable accuracy. Even during its initial test observations, Rubin identified 46 RR Lyrae stars. Over the course of its full survey, scientists expect that number to grow to nearly 100,000. Many of these ancient stars lie far beyond the bright central regions of our galaxy, scattered throughout the Milky Way's outer halo or even extending toward intergalactic space. By tracing their locations, astronomers can assemble a detailed skeletal map of our galaxy, exposing faint streams of stars left behind by ancient galactic collisions, uncovering hidden dwarf galaxies, and revealing the true three-dimensional structure of the Milky Way's outermost regions. For decades, these distant parts of our galaxy have remained extremely difficult to study because the stars are both incredibly faint and widely dispersed across the sky. Rubin's extraordinary sensitivity and massive field of view are finally making those hidden regions accessible, opening an entirely new window into the history and evolution of our own galaxy. Rubin's enormous field of view, deep imaging, and repeated sky surveys transform difficult observations into routine discoveries. Instead of simply taking pictures, it maps the Milky Way's hidden structure and reveals ancient traces of our galaxy's history. By the end of its 10-year mission, Rubin could completely reshape our understanding of the universe. At the heart of the observatory is the world's largest astronomical camera, a 3.2 billion pixel system with 189 sensors and giant precision lenses. It captures ultraviolet, visible, and near-infrared light with incredible clarity, producing rich scientific data rather than ordinary photographs. Unlike Hubble, which focuses on small areas in extreme detail, Rubin captures vast regions of the sky in a single image, covering an area equal to about 40 full moons. Hubble reveals fine details, while Rubin shows the bigger cosmic picture, making the two telescopes perfect partners. Rubin's data is also available through SkyViewer app, allowing anyone to explore its massive images. Users can zoom from giant cosmic landscapes down to individual stars, opening the door for citizen scientists to help discover supernovae, comets, and other rare cosmic events. Rubin's open access data is making astronomy more accessible than ever, allowing both scientists and the public to explore the universe together. With its rapid 3-day sky scans, the observatory can detect asteroids and even rare interstellar objects much earlier than previous telescopes. During its first tests alone, Rubin discovered over 2,000 new asteroids, proving its extraordinary ability to track fast-moving objects. These discoveries could help scientists study material from distant solar systems and answer long-standing questions about mysterious visitors like Oumuamua and 2I/Borisov. More importantly, Rubin is changing how we observe the universe. Instead of isolated snapshots, it creates a constantly updated time-lapse view of the sky, capturing supernova, gamma-ray bursts, and other cosmic events as they happen. Its observations are already helping map the Milky Way, uncover hidden structures, and reveal the universe as a dynamic, ever-changing place. The Vera C. Rubin Observatory is more than a telescope. It's the beginning of a new era in astronomy. Over the next decade, it could transform our understanding of the cosmos faster than ever before. If you're excited to follow Rubin's incredible discoveries, don't forget to subscribe and turn on notifications. The next image it captures could change not only astronomy, but our understanding of the universe itself.